Our today's talk is about the addition of two angular momenta. Let's form a general formalism. Consider two angular momentas J1 and J2 which belong to two different subspaces 1 and 2. The components of J1 and J2 are they satisfy all the commutation relations for the angular momenta, that is J1x, J1y will be iota h bar, J1z, J1 square and J1z, they are compatible with each other. J2x, J2y is equal to iota h bar J2z, J2 square and J2z, they are compatible with each other. That is, this is equal to 0. Since J1 and J2, they belong to two different subspaces, so they are compatible with each other. That is, J1i and J2j is equal to 0, ij is xyz. That is, components of J1 and J2, they are compatible with each other. Now, since J1 square and J1z, they are compatible with each other, so they will have simultaneous eigenket. We write it down by J1 M1. Similarly, J2 square and J2z, they are compatible with each other, so they will have simultaneous eigenket. We write this simultaneous eigenket as J2M. Now let's write down the eigenvalue equations, the equations when these operators they act on the ket. We will be getting when J1 square acts on J1 and M1, we get the value equal to J1 into J1 plus 1 h bar square into J1 M1. When J1z acts on J1 M1, we get value as equal to M1 h bar J1 M1. Similarly, when J2 square acts on J2 M2, we get the value equal to J2 into J2 plus 1 h bar square J2 M2, and J2z when it acts on the ket J2 M2, we get the value to be equal to M2 h bar and J2 M2. The dimensions of the space to which J1 and J2 belong, that is given by 2J1 plus 1, this will be dimensionality of the space to which J1 belong, and dimensionality of the space to which J2 belongs is given by 2J2 plus 1. They are represented by the matrices of the rank 2J1 plus 1 into 2J1 plus 1 and 2J2 plus 1 into 2J2 plus 1 respectively, and the basis for these are J1 M1 and J2 M2. Now let's consider the two particles together. Once we consider the two particles together, then the four operators, they form a complete set of the commuting family. That is, the four operators J1 square, J2 square, J1z and J2z. Now these operators, they form a complete set of commuting operators. And so if they are compatible with each other, that means they will have simultaneous eigenket. That simultaneous eigenket is written as J1, J2, M1 and M2. In such a way that when J1 square, it acts on the ket J1, J2, M1, M2, we get the value to be equal to J1 into J1 plus 1 h bar square into the simultaneous eigenket J1, J2, M1 and M2. When J2 square acts on the ket J1, J2, M1, M2, we get the value J2, J2 plus 1 h bar square into J1, J2, M1 and M2. When J1z acts on the ket J1, J2, M1, M2, we get the value M1 h bar into ket J1, J2, M1 and M2, and when J2 Z acts on the ket J1, J2, M1, M2, we get the value M2H bar into J1, J2, M1 and M2. This ket, now all these kets, they form a complete set of orthonormal bases. When we say that they form a complete set of orthonormal bases, that means they are normalized and they are orthogonal. Two kets are orthogonal to each other and all the kets are normalized. From there, we get the closure property, which states that outer product of the kets J1, J2, M1, M2 with J1, J2, M1, M2, sum of all these when M1 varies from minus J1 to J1 and similarly M2 varies from minus J2 to J2, this is equal to identity operator. And orthonormality tells us that inner product of the kets J1 dash, J2 dash, M1, M2 and J1 dash, J1, J2, M1, M2 is equal to delta J dash J delta. We will have the inner product with the two. The inner product of this set into the inner product of the second, that is J1 dash with the J1 dash and J1, J2, M1, M2 with itself J1, J2, M1, M2. This will be equal to delta J dash, J1 dash, J1 delta J2 dash, J2 delta M1 dash, M1 delta M2 dash, M2. Let's once again do this orthonormality condition. This orthonormality condition says that the two kets are orthogonal as well as normalized. So we will write it as J1 dash, J2 dash, M1 dash, M2 dash with the J1, J2, M1, M2. This will be equal to delta J dash J delta J1 dash J1, J2 dash J2 delta M2, M1 dash M1 and delta M2 dash with M2. This is the orthonormality property. And the basis which spans this space is given by J1, J2, M1, M2. Dimensionality of this will be 2J1 plus 1 multiplied by 2J2 plus 1. Now let's go back to the problem of adding two angular momentas, that is J1 and J2. J is equal to J1 plus J2. Now the problem of addition of these two momentas, it consists of finding the eigenvalues and eigenvectors of J square and Jz. That is, we have to find the eigenvalues and eigenvectors of J square and Jz in terms of the eigenvalues and eigenvectors of J1 square, J2 square, J1z and J2z. let's see once again this step, the problem of adding two angular momentas J1 and J2. It consists of finding the eigenvalues and eigenvectors of J square and Jz in terms of eigenvalues of J1 square, J2 square, J1z and J2z. Now we can very easily ascertain that Jx and Jy, this will be equal to iota h bar Jz. That is, the components of total angular momentum after addition, they are not compatible and they follow the same commutation relation. J1, Jx and Jy will be equal to iota h bar Jz, and J square, which is equal to J1 square plus J2 square plus J1 dotted J2 plus J2 dotted with J1, but they are compatible, so we can write it down that it has 2 J1 dotted with 2 J1 dotted with J2, and J square, it is compatible with J1 square, and J square is compatible with J2 square. J square is compatible with Jz. J1 square is compatible with Jz, and J2 square is compatible with Jz. These are the commutation relations which we will be using. But in spite of the fact that J square is compatible with Jz, we get that J square and J1z, they are not compatible. Similarly, J square and J2z, they are not compatible. These are the commutation relations which can be easily proved that Jx and Jy, it is iota h bar Jz. J square and J1 square, it is 0. J2 square and Jz, it is 0. They are compatible. J1 square and Jz, they are compatible. J2 square and Jz, they are compatible. J square is not compatible with J1z. Similarly, J square is not compatible with J2z. Using these commutation relations, now we are in a position to write down the simultaneous eigenket. We have seen that J1 square, J2 square, J square and Jz, they form a complete set of operators which are compatible with each other. So they can be simultaneously diagonalized, or they will have a simultaneous eigenket. Let that simultaneous eigenket, they will have simultaneous eigenket. Let that simultaneous eigenket be J1, J2, J and M, in such a way that when J1 square acts on J1, J2, J, M, we get the value as J1, J1 plus 1 h bar square into the state J1, J2, J and M, when J2 square acts on the state J1, J2, Jm, we get the value as J2, J2 plus 1 h bar square, and the eigenstate is J1, J2, Jm. When j square acts on the state j1, j2, jm, we get the value j into j plus 1 h bar square into the state j1, j2, jm, and when jz acts on the state j1, j2, jm, we get the value as mh bar into the state eigenstate j1, j2, jm. For every value of j, we will have 2j plus 1 values of m, varying from minus j to plus j. This set of vectors, it forms a complete orthonormal basis. Now, for convenience, I am writing this simultaneous eigenket by Jm. It is understood that I have got the value J1 and J2 with it. So this set of vectors, it forms a complete orthonormal basis. That is, if we write down the outer product of Gm with Jm, I get it to be identity operator, where we'll have summation over j and m varies from minus j to plus j. And inner product of the ket delta j dash, inner product of the ket j dash m dash with jm, this is delta j dash j delta m dash m. We will have a product space, total space, whose dimensionality will be given by 2j1 plus 1 into 2j2 plus 1. This will be the dimensionality of the total space where we are adding the two angular momentas j1 and j2. Now, they can be connected by means of a transformation using the identity operators. We have got this simultaneous eigenket. We want to know its value, and these kets can be written in terms of, we have got Jm and we want to relate it with J1 and J2. To relate it with J1 and J2, we can use the transformation operator. Now our main aim is to get these kets. To get these kets, we use the method of transformation operators. Let's use the identity operator as the outer product of the ket J1, J2, M1, M2, J1, J2, M1, M2. Let's use this identity operator and multiply this ket, which is simply written as Jm. So, I have used this identity operator here. That is, let's once again see how have I written this J1, J2, Jm ket. The ket J1, J2, Jm. I want to relate it with the states J1, J2, M1, M2. So to write it down in terms of M1, M2, what I do, I use identity operator. M1 summation is over M1, M2, and the identity operator is J1, J2, M1, M2, and then J1, J2, M1, M2, and then the same ket, the shorthand of which is Jm only. As this ket as well as this ket. These two kets are both normalized, so this transformation must be unitary transformation. Because this is normalized ket, this is normalized ket. So this transformation must be unitary transformation. Now let's have a look at it. A closer look at it tells us J1, J2, M1, M2, then J1, J2, M1, M2, and here I had Jm. Let's have a closer look at it. I have got two summations here. These are nothing but the expansion coefficients. These are the expansion coefficients which connect Jm with the state J1, J2, M1 and M2. We have written this ket in terms of this ket with the help of these expansion coefficients. These expansion coefficients are called CG coefficients. So here we have defined the CG coefficients. CG coefficients are nothing but the expansion coefficients when we write down the state which is due to the sum of these two states in terms of these two states. So these are the CG coefficients. The problem of angular momentum addition, which was J is equal to J1, J2, now it has been reduced to finding these expansion coefficients, that is in finding the CG coefficients. Let's see what are the properties of these CG coefficients. The first property associated with these CG coefficients is that these CG coefficients are real. So the first property is that we consider that these CG coefficients, these expansion coefficients, they are real. Second property associated with these CG coefficients is that CG coefficient vanishes until it vanishes, unless m is equal to m1 plus m2. So this m must be equal to m1 plus m2, only that CG coefficient will exist. The CG coefficient vanishes, the third property is the CG coefficient vanishes unless we say that it vanishes unless J lies between J1 minus J2 and J1 plus J2. Only those values of J are permitted which have value between the difference and the sum of two angular momentas. This is the second property associated with the CG coefficient. Third. Till now we have associated three properties with the CG coefficient. One is that the CG coefficients are real. Second is that CG coefficients vanish unless we have got m is equal to m1 plus m2. Third is that it vanishes until it is there only for J value lying between J1 minus J2 and J1 plus J2. CG coefficients, we have seen that this is a unitary transformation, and CG coefficients, they form a unitary matrix. The elements of the unitary matrix are taken to be real by convention. As I have said that they are taken to be real by convention, that means if you take the inverse of it, it will be same. Even if we take the inner product of Jm with J1, J2, M1, M2, it will be same as the inner product of, that means even if we take the bracket vector, we convert this bracket vector into ket vector or this ket into bracket, the inner product will be same. So the the last property is that the all unitary matrix, they are orthogonal. So we will have the orthogonality condition also. Orthogonality condition says that J1, J2, M1, M2 into J1, J2, Jm into J1, J2, M1 dash, M2 dash and J1, J2, J dash, M dash. If we take these two inner products, summation is over M1 and M2, this will be equal to delta MM dash, M1, M1 dash and delta M2, M2 dash. Likewise, you can take with the Jm also. We can say that the inner product of J1, J2, M1, M2 with J1, J2, Jm modulus square, this is equal to 1, which is the normalization condition of J1, J2, Jm. Now we have defined the CG coefficients. Our next talk will be to calculate these CG coefficients for different values of J.